This video will be the first in a series on what are known as differential equations. And what I mean by that is any equation relating a function to its derivatives. And our goal here will be to learn how to solve first order differential equations, which sounds a lot more complicated than it's actually going to be. And since the mechanics required to reach our goal are not overly complicated, I feel the best way to show this is just by jumping into a problem. So I'm going to read through this, and as I do, I'm going to turn what seem like complicated directions into relatively simple ones. And you'll see that this is actually a process that you've done before. So this problem states, solve the first order differential equation, and that whole phrase just means find the antiderivative, or integrate. And what we're integrating is this equation, dy over dx equals negative x over y, an equation describing the change in y over change in x, or the slope of some graph. And note here, what this means is that the slope is defined this way for any ordered pair. If I want to know the exact rate of change, or the instantaneous rate of change at any point, x comma y, it would be negative the x value over the y value. And so given the exact variables that describe my relationship, I can even say that the antiderivative I want will be some equation y equals f of x. And given y of 0 equals 2. And for this, recall that if we get any antiderivative or indefinite integral, we always have that plus c at the end of it because we don't know the exact function that came before it. That's our condition to get rid of the plus c. An exact ordered pair that we know exists for this relationship. In this case, 0, comma 2. And so I'm going to rewrite this derivative equation and jump right into how we're going to solve it. And so the first step is to get everything with a variable x to one side, everything with a variable y to one side. Thinking about trying to go for the antiderivative, I can integrate something like f of x and talk about the area under that curve in relation to, or with respect to, the x-axis. Or I could integrate something like a function of time with respect to an axis that involves time. These are both okay. What I couldn't do would be something like integrate a function f of x with respect to time. I'd be talking about a function that requires an input of x, but talking about a horizontal axis that involves a variable t. And thinking about this as an area problem, I wouldn't even be looking on the same graph for these two pieces. Wouldn't make much sense. And so this first step is just algebra. Think about every piece, and these are both just fractions. Treat the dy and the dx as little mini variables that you can move around. And this one's actually easy enough to do just by cross multiplying. And I can turn this equation into y dy equals negative x dx. And a key little note as we get into working on problems like these, leave extra constants with the independent variable. So in this case, our x. Just because eventually, like we saw up here, we're going to need to solve for y. We want a function y in terms of x. So we don't want to put extra stuff on the y side to make things more complicated. And step 2 states we're going to integrate both sides, or find the antiderivative for our y function with respect to y and our x function with respect to x, just using our basic rules for antiderivatives. So on the left side, we'll get 1/2 y squared plus c equals, on the right side, we're going to get negative 1/2 x squared, and it's also going to have a plus c. Now these don't necessarily have to be the same number, so I'm going to denote them c1 and c2. And what's nice about this is actually, knowing we're going to want to get y by itself, I could move this c sub 1 over to get rid of it from the y side. I'll be taking one constant minus a different constant, and realize that this is just one big constant, or one big c. And really my equation will just become 1/2 y squared equals negative 1/2 x squared plus some constant. And make a note, now that you've seen why I can do this, only put your plus c on the independent side. Don't worry about putting it on the dependent variable side. Step 3, solve for the dependent variable. In this case, I can see one thing I can get rid of right away is this 1/2, just by multiplying the entire equation by 2. This will give me y squared equals negative x squared plus, and notice how I'm going to be multiplying this constant by 2. But note that this is still a constant. So I don't need to call it 2c. I can just say that 2 times a constant is still one big constant. And finally, we'll take the square root of both sides. Notice how I have an issue here though. A square root in solving would give me a plus minus, which would not make this a function. This must be plus or minus, not both. And we'll resolve that in our last step. In that last step, find c if you're given a condition about this original function. And we were. We knew that our y value is 2 when our x value is 0, which tells me that my outcome had to be positive, so I just want the plus and not the minus anymore. And now I've resolved this whole problem with not being a function. Completing this and solving for c, we will get that 2 equals the square root of c, and c equals 4, giving our final equation as y equals the positive square root of negative x squared plus 4. And that is how you solve a first-order differential equation. Looks a lot like doing any other antiderivative, except we need to integrate 2 different variables in the same problem. Much the same way that we worked on differentiating 2 different variables with implicit differentiation. Please move on to the next video when you're ready. Thank you for watching.